Hi, and welcome back to our discussion of atomic structure and models of atomic structure at the APIB HL level. Now, I want to just do a quick summary and example to tie together the concepts that we've discussed so far. I found this really nice picture on the internet that I hope will summarize some of the terms you've been hearing me use and will firm up your understanding of those terms. Here's the reference for that. Remember, we talked about the ground state. This is showing electron densities. It's shaded the regions in space where an electron is most likely to be found. And the ground state, remember, all attractions have been maximized and all repulsions have been minimized. They're at their minimum. And when we do an electron configuration from the periodic table, that's what we're doing. We're getting at that ground state electron configuration. An excited state is when energy has somehow come into an atom and electrons have gained energy. But note that in an excited state, those electrons are still attracted to the atom. We're still talking in general about a neutral atom. Certainly we could have ions that are excited, but that's not your most common questions that you'll come across. So it's gained energy, but it's still sensing that attractive force to the nucleus. Remember the nuclear charge given by Z. This shows ionization. At this point, an electron has gained energy, but at this point, the electron leaves that sphere of attraction. I can't spell to get today for some reason. I think I'm talking and writing at the same time. The electron leaves. So we have formed a cation, which is why we call it ionization. We're forming a cation in that case. So that illustrates the different types of processes that we've seen so far. Now I want you to be able to analyze electron configurations as well. So if we look at this electron configuration, notice 1s2, 2s2, 2p6, 3s2. Those are filled. They are, for one thing, those sublevels are filled. And for another, they're filled in the correct order that the periodic table and Aufbau's principle tells us to do that. And then 3p1, so that would be aluminum, I believe. I'd have to look at a periodic table to triple check that, but it should be aluminum. And it is the ground state. Whoops. It's the ground state of aluminum. Now, if you look here, notice that instead of filling the 3s, an electron has moved up a higher energy level. That's why it's excited. An electron has left in this case. Now, if we're talking, it's aluminum is right here. Now, if we look at this, and we would have to tell you somehow we were still talking about aluminum, otherwise you would just think it's the noble gas. But do you notice in this case we have lost our outer S and P electrons. So if I'm telling you this is definitely aluminum and I'm missing 3 of the electrons, that means we have the aluminum 3+ ion. We would say it has a +3 oxidation, but when we write it as an ion, you put the number before the charge. So that's how we would write the aluminum 3+ ion. Now, this is showing you one that's just plain wrong. And I want you to take a look at why. We have 1s2. Now, this 2p5 would be okay because you would think, oh, well, maybe it's just an excited state. Maybe one of the 2p's went to the 3p. So this portion of it here would make you think, whoops, I tried to change colors, blew it. That portion would be just as if it was an excited state, if that's all there was. But there's a bigger problem here that tells us that it is not simply an excited state. And that's this right here. Because it says 2s3. And an S sublevel can only have 2 electrons. Otherwise, there's just too much repulsive forces going on. So an S sublevel can only have 2, and this shows it 3. That's why it's just plain wrong. Now, some of you may, in your mind, have asked the question, well, how the heck do we know all this? How do I know that what this crazy old lady teacher is telling me is true? Well, in class, we're going to explore, it's an older technique, but I think it's a valuable introduction into more spectroscopy, and it's photoelectron spectroscopy that helps us show, that demonstrates that the electron configurations from the periodic table are by and large correct. Of course, in life, there's going to be some deviations. We're talking about models, and often with models, we follow some trends and make some simplifications. But photoelectron spectroscopy is going to show us not only that most of our electron configurations from the periodic table are correct, but it also helps us understand ion formation. So until then, this is signing off.